Okay, we're back from the break and we're going to start looking at power dissipation. Typically, I put power in quotes because it's not really power that's being dissipated, but rather energy, but we call it power dissipation. CMOS has initially and ideally been considered attractive because it's a low power kind of technology. That means that when a gate is not switching, there's no DC path from VDD to ground. There is still, however, leakage currents. These can be a result of reverse bias PN junctions or leaky gate dielectrics themselves because the gate dielectrics are so thin. In the past, this has usually been negligible for older technologies unless perhaps your design relied on charge storage such as a dynamic RAM. The later technologies, the currents can be quite significant, and as I said, these are a consequence of very thin gate dielectric materials and other scaling things that happen, such as the highly doped junctions, which can lead to quite significant currents that are flowing through the device. The main power consumption, however, is still the direct result of switching, and that is charging and discharging a capacitive load. Power would be lost in the form of heat typically, that's I squared R, perhaps some radiated in terms of infrared. For our purposes, power dissipation is going to be considered to be in two components, a standby or a static current, or a dynamic current results from currents that result from switching and the consequence the power dissipated at that point in time. This also leads us to a test that we could see if the chip is good, and basically it's called this IDDQ test, and this is this expression for it. We're looking at the current through the device when it's quiescent, so nothing changing, nothing happening, and we just try to monitor it to see how much current is flowing through that device. If it's above some threshold, there may be something wrong with that chip and perhaps not worthwhile shipping it. So with respect to the static power dissipation, typically we're looking at this situation. Nothing is happening on the inputs of these gates, so typically what's is going to be, one of these gates is going to be open and one of these is going to be closed, and the input is going to be either tied to ground or tied to VDD. I should say the output would be tied to ground or VDD. So in theory, there's a good low static power dissipation in CMOS. This implies there's no path from VDD to ground, and the DC power dissipation would be negligible. It's not exactly zero, and you can sort of convince yourself of that by considering the fact that there's a bunch of reverse bias PN junctions all over the chip, and a diode current to first order might look something like this expression down here, where JS is this reverse bias saturation current. Now there's also leakage current through the MOSFET devices themselves. Anyway, we want to try to get an estimate for what this power dissipation might look like, and so we're going to, maybe try to consider the reverse bias saturation current density. We'll consider total chip area and try to get a ballpark of what this static power dissipation might look like. For older chips, it's probably 20 years old or so. Junction area might be on the order of 0.2 centimeters squared, reverse bias saturation current on 10 to the minus 8 amps per square centimeter, and VDD at 5 volts. So that basically meant there was like 10 nanowatts, so really not much current at all. Maybe a little bit of temperature dependence here, might reach 100 nanowatts for 20 degrees C above ambient. So really not much power in those older chips, because that sort of led to the IDDQ type of test. It's still useful because obviously if you have lots of quiescent current flowing, there's something going wrong. But in this particular case, you'd power up the chip, the inputs would be stable, and you just check if you're drawing too much current. Here's an example for a 180 nanometer process, so a few years old, but not ancient. IDDQ values for normal operating conditions, where VDD was 1.8 volts and the temperature was 25 degrees C, and then a case where it was stressed to 2.4 volts and stress and temperature at 150 degrees C, and this is for a 1 million transistor chip, was estimated to be 0.13 milliamps and 28 milliamps respectively. So that was, I guess it's around 2003-ish, so it's still becoming significant, certainly when the chip is stressed, even more so. These types of tests may also provide an idea for how long the chip will last if there's too much static power dissipation. If you go to a more modern technology, like a 45 nanometer node technology, this came from that Semiconductor Industry Association roadmap. The leakage there was 0.06 microamps per micron. And consequence, if you sort of calculate it for that node technology, whether it's accurate or not doesn't really matter. It sort of comes out to something on the order of 130 amps per square centimeter, which is pretty significant. So for a 5 centimeter square chip, which is very large, 1% junction area, which is probably quite small, and half of those devices leaking at any given time, i.e. in reverse bias, you end up with something on the order of 3¼ watts. So it's becoming quite significant. So that was a junction, the gate leakage for the 45 nanometer. Again, according to that roadmap for that technology, estimated at 200 amps per square centimeter for a 5 square centimeter chip with 0.1% gate area and half the devices on any time. The power then came out to something on the order of ½ watt. So these two would actually combine to tell you what the static power dissipation was. And here's an in-class assignment 5.7. You know, how many amps does that relate to? And what does that have to say about IDDQ or an IDDQ test for this type of technology? So try to come up with a reasonable answer for, well, certainly a definite answer for the first part, maybe a reasonable answer for the second part. So the static power dissipation in a CMOS circuit, in summary here, the past it was quite small, virtually no DC path from VDD to ground. Today's newer chips, standby power can be significant. It's still going to be a fraction of the dynamic power dissipation, and though it's small, the static or standby power consumption has to be designed for. And in particular, as people move toward more battery operated devices, it sort of leads to a new area of design specialization for low power applications. Can't get to the next page. Okay. Here we go. This is sort of one of the students told me a long time ago, sort of making these very crude assumptions. He sort of said it was like estimating the telephone traffic in New York City through one big phone. That may well be the case. It's not very accurate, but the point is it really can't be ignored. So the other part of the power dissipation we're going to look at is more interesting. It's the dynamic power dissipation. And here's the scenarios we look up in this particular case. Let's say we turn this inverter, there's an inverter under here. We turn it on, so this NMOS transistor is going to be on. It's going to discharge the output capacitor, or the load seen by that inverter. And during that process, there's a brief period of time in here that you would say that both of these devices are on. So I sort of represent this as having a flow from VDD to ground, as well as the current that's discharging that capacitor. The same thing happens when you charge up the capacitor. Some region in here, both of these devices are going to be on. These don't have infinite slew, as you can see. And as a consequence, both of these devices will be on momentarily while you're charging up that output load capacitor. So during discharging as well as charging, these two are backwards, you're going to see that you have some power dissipation. So we have current flowing from VDD to ground. And basically that's this momentary DC path from VDD to ground. This is sort of the trajectory we would look at to try to estimate it. So at some point in time when we're switching from V out equal VDD to V out equals 0, let's say we're discharging the capacitor, we're going to basically make some kind of a trajectory through the IV characteristic for those devices. And we're going to be able to estimate then what an Imax is going to be. So the maximum current is going to happen somewhere in this mid-range of switching, if this is what our input waveform looks like, and we're going to get a blip in the current, and we'd be able to calculate what the power dissipation there is at any point in time. It's just the switching current times the supply voltage, not Vn. So sometimes when you see a graph like this, you're tempted to multiply this current by this voltage, but remember, it's coming from the power supply. The second thing we're going to be interested in is charging and discharging CL, and this accounts for the energy losses as CL is charged or discharged, because we're charging it and discharging it through either an NMOS or PMOS device. So previously we're interested in rise and fall time. Now we're interested in the power that's dissipated by those devices while they're being switched. And that brings us to another